Hello, welcome back. This is Calculus by Dr. Oz. Today we have an exercise where we're going to practice the so-called ratio test. We have four hand-picked exercises. I'm going to explain the ratio test in the video for each case, but I'm going to quickly have a run-through of that. So for you to be able to apply the ratio test, first of all, you have to have an infinite series with non-zero terms to start with. And there are three major cases you can fall into. One is absolute convergency, the other one is divergency, and the last one is inconclusiveness. Okay, so for all of those three cases, you're going to check only one limit. Okay, so what is that limit? Limit of the absolute value of the ratio of two consecutive terms. And the limit is on n, so that ratio between two consecutive terms as n approaches infinity is what we're checking. So if that limit turns out to be less than 1, that's the best case scenario. You just nailed the absolute convergence, you can go home. The second case is also another good case, because if you just have the limit strictly greater than 1 or even infinity, or doesn't exist, sometimes we call it doesn't exist, right? So in that case, you have the divergency, yes, you can go home. All right, what is the worst case scenario? Well, the worst case scenario is when that limit is exactly equal to 1. Then the test is inconclusive, means like there's no outcome of this test. So that means you are going to explore other tests to deduce about the convergency of the given infinite series. So this is exactly what the ratio test is, and I'm going to give you the hints about like when to apply the ratio test to certain infinite series. So you will get the hints in the video, and I'm going to split this video into four. That I will solve each case in separate videos to make the videos shorter. All right, so we have four of them. We have a long way to go. Let's get started.
Let's start with 2 to the n, 2 to the n plus 2 factorial. As in the description, I'm going to look at the limit of the absolute value of an plus 1 over an. Okay, so let's just do that. So who is an to start with? Well, an is 2 to the n plus 2 factorial. Okay, and therefore an plus 1 over an is equal to 2 to the n plus 1 over n plus 3 factorial. So I'm going to replace n by n plus 1 in the description of an, divided by 2 to the n plus 2 factorial. Okay, we have two fractions, and the bottom one is flipped over to simplify this expression. At this moment, you are using a lot of algebra for cancellation, so you better remember the definition of the factorial. Okay, so for example, there are two things here to simplify this expression. One is that 2 to the n plus 1 can be written as 2 to the n times 2 to the 1, which is in fact 2 times 2 to the n. Okay, and also n plus 3 factorial is in fact n plus 3, and going all the way to 1, so you just take the product of all integers starting from n plus 3 to 1, but starting from n plus 2 to 1, it's n plus 2 factorial. So that part is n plus 2 factorial. So in other words, n plus 3 factorial is just n plus 3 times n plus 2 factorial. Okay, so let's use these two properties here. Okay, so I'm going to switch 2 to the n plus 1 to 2 to the n plus 1 times 2, which is 2 times this, right? Okay, and the bottom here is n plus 3 times n plus 2 factorial. Okay, times n plus 2 factorial 2 to the n. Okay, so the good news here is that 2 to the n here cancels this 2 to the n. Okay, I think I should use smaller stroke here so you can actually see. Here we go. This one cancels this, and n plus 2 factorial cancels this n plus 2 factorial. At the end of the day, I have 2 over, 2 at the top, and at the bottom you have n plus 3. Okay? All right, let's go back to the expression again. So we're going to take the absolute value of an plus 1 over an and pass the limit. Okay, let me just clean this part so that we save some space here. Okay, so I'm going to look at the limit of the absolute value of this expression, but this expression is positive no matter what for any n, right? 2 over n plus 3 is always positive, so I don't need to worry about the absolute value sign, so I'm just going to pass the limits. And this is something that we did in the beginning of calculus, that as n approaches infinity, 2 over infinity is 0, right? The limit of that is 0. And the good news is that 0 is a number less than 1, okay? So that's a number less than 1. The conclusion here is that this series is convergent. Okay. Y, again, the limit here is 0, which is less than 1.